Okay, so this presentation is a deep dive on the OpenRack V3 power shelves, as well as the power supply and the rack controller. My name is Ralf Pieper. I'm the R&D director and working for Delta Energy Systems, and I'm located in Germany.
Hello, everyone. My name is Harry Soin. I'm from Artisan Embedded Power, which is a division of Advanced Energy. I'm a senior technical marketing director responsible for the hyperscale space, and I'm located in San Jose, California.
My name is Lam Vu. I'm an R&D director of a design center, a Lion Design Center in Plano, Texas. And I'm part of the presentations of this deep dive on OpenRack V3 PowerShell.
Okay, so this presentation will be cut into 3 parts. So I will do the first part. I will present the 2OU PowerShelf. So I'm talking about the mechanics, the busbar and connections, as well as the current share between the power supplies. Then Harry will present the 1OU shelf. He will also explain the mechanical details, thermal management, scalability, and control options. And at the end, Lam will present details regarding the rectifier, so the power supply, and the PMC. This is the power shelf controller. So I will start with this 2U or 2OU power shelf. So here we see a short spec. So the shelf has a dual AC grid input at the rear, so 2 times this Harting AC connectors, which can deal both with a Y grid and delta grid. So a 4-wire or a 5-wire grid you can connect. So it's worldwide usable. And it has 12 slots where you can insert the 3 kilowatt OCP V3 power supply. So the output voltage of the rectifier is a fixed 50 volt if the power supply is connected to AC, and it's a 48 volt if the battery is connected or the BBU is in operation. The total output current is 720 amps, so it's 2 times 360 per layer, and each input grid of the rear is feeding 6 power supplies. So the left connector feeds 6 and the right connector feeds 6 power supplies. The total height of the shelf is 2 OpenU, which is 96 millimeter. And the total installed power is 12 times 3 kilowatt, so it's 36 kilowatt. And in the 2N redundancy, you can use 18 kilowatt. And the shelf hosts this PMC card. So this is the power monitoring controller. So this is in the front left. And the overall size is 21-inch wide, so 533 millimeter. The height is 2 OpenU, 96. And the depth is 666 millimeter from front to the rear sheet metal. And the busbar clip is compatible to the OpenRack busbar design. So this page shows the PMC card, so the power management controller, which is located here on the bottom left. And it's hot pluggable and hot unpluggable. So you can plug in or remove it during operation, and it will not interrupt the operation of the shelf. So it still continues to run. The controller on the PMC, this gets the power from the 50 volt bus voltage from the rear. So it has an own DC-DC converter on board. And the communication between the controller and the power supplies is I2C, internal in the shelf. And to the external, it's RS485, the upstream communication. And it has 4 RJ45 ports in the front with different signals. So this is specified in the PMC spec. And the size is, the width is 45.7 millimeter. And the depth or the length is 343.9 millimeter. And it has a card edge connector, which plugs into the mating card edge connector here. So for the output bus bar, we use 2 times on 500 amps a bar clip BK500 from FCI. So each layer has one of these 500 amp bus bar clips. And to accomplish the 3 millimeter horizontal and vertical float, which is required by specification, we are using this braided copper to have a flexible output bus bar. And this is very lean, so we don't block too much airflow with this braided copper. And the current, the output currents of these 12 power supplies, this is collected by the bus bars. You can see here in the rear. And the currents are collected together. So it's 330 amps per 360 amps per layer. And then it will feed into this braided copper. So some details to this AC input, which I mentioned at the beginning. So on the rear side, we have 2 of this Harting 170 amp connectors, and each one has 7 pins. In the Y grid, we have line 1, line 2, line 3, and 3 times neutral. So the power supplies run between line and neutral. And they get this 200 or 277 volt AC. And we have the 7th pin is PE. So in a delta grid with 3 wires without neutral, the units are running line to line. So line 1 to line 2, line 2 to line 3, line 3 to line 1. And we get the line-to-line voltage in the US, it's normally 208 volt AC. So that means the power supply itself always is running at 200 to 277 volt nominal. So now some current share basics. So there are popular current share techniques which are normally used in power supplies. So one side is the active share, which is often used at low voltage. So for example, for 12 volt outputs. And the other technique is a droop share. So here we see the difference. So we have a constant voltage over the output current in the active share. And we have a variable output voltage over the current in the droop share. So at light load, output voltage is slightly higher than the set voltage. At 50% load, it's exactly the set voltage. For this example, it's 50 volt. And at full load, you have a slightly lower voltage than the set voltage. So this actually behaves like a battery with the output resistance. Where else here, for the active share, you have always a constant voltage. So there is no variation in the voltage overload. And of course, there are advantages and disadvantages. So the advantage is, as I said, a constant voltage and very tight regulation. And this has very good steady state performance. The disadvantage is that it can oscillate because it's from, it's inherent unstable. let's say, and you need a current share line between the power supplies. So there is a physical connection between the power supplies to transmit the current share information. And on the Drupe share, we also have advantages and disadvantages. So the advantage is it's inherent stable compared to the active share, and it has very good dynamic performance, and it's very fast for load steps and so on. The disadvantage is you have a share error if the set voltages of the two units are not perfectly equal or calibrated, let's say. And here you see this in the picture. I draw a second line, so from a second unit where the output voltage is slightly moved in parallel, and then this would be the perfect share, the red dot, and then in the blue case it would move not 50-50 share, so it's here around 75% to 25% share. So as we see, both have advantages and disadvantages. And in the OCP V3, we have combined both techniques, and actually we are using the advantages from both techniques. So we will have a 1% Drupe, which is 500 millivolt, so 1% of 50 volt. And we have this active shallow current share. So the shallow means that there is only a very slight and slow adjustment due to the active share bus. So this cannot lead to oscillations because the influence is very, very minor of this active share. So the Drupe share is fast and dominating during load steps. So we will have a very good load step performance because this active share is not needed to be active during load steps. So this is passively done by the Drupe. And the I-share connection, this will just compensate the voltage drops across the bus bar between the units. So the units which sits at the outside of the shelf, they have a longer way to the bus bar clip in the middle. So there will be a voltage drop, and this voltage drop is compensated by the active share. So it will behave very good in dynamics because we have the Drupe and we have a very good static regulation due to this active share. So this was my part of the presentation, and the next part will be presented by Harry.
Ralph just spoke about the 2 OU power shelf, so I'm going to take you through the 1 OU power shelf. The agenda of my talk is divided into 3 parts. I will talk about the mechanical design first, followed by the thermal management, and then I'll conclude with the scalability and the control options of the design. So Artisan has designed the 1 OU power shelf, 2 OU power shelf, and the PSUs that go in them. Artisan will also be providing a PMC once the specifications are confirmed. So here we are going to deep dive into the 1 OU power shelf, and we will now cover briefly the details of the input and the output. You know, the power shelf output is 48 volts, and each PSU is 3 kilowatts. So the shelf is capable of total power of 18 kilowatts or 15 kilowatts in N+1 configuration. The shelf has the Amphenol bar clip connector, which is rated at 500 amps. The input power is, is totally 3-phase from 277/480 volts. And the input connector on the power shelf is a positronic 7-pin connector. So the supply cord can be configured as a star, delta, or a single phase, and I'll walk you through briefly in my next slide. Another inherent advantage here is there is a direct connection from the tap box. So we do not need a PDU here. Now, in terms of composition, this power shelf can accommodate 6 rectifiers. Each one is 3 kilowatts. The shelf and the rectifiers have the Amphenol Power Blade Ultra connector. This shelf also accommodates the shelf management controller. There are 4 RJ45 connectors in the front, and they are also repeated on the back. So as I mentioned in the previous slide about the connections, that how the supply cord can be configured for 3 different types of operations. And this slide here gets into a bit of detail into that. The line pairs are 1, 2, 3, 5, 6, 7, and 4 being the protective earth. So if you look at the picture on the left-hand side here, as you see, this is a star connection where pins 2, 5, and 7 are connected together to form a star, whereas pins 1, 3, and 6 are the lines. On the right-hand side is the delta connection. The adjacent pins are connected together to form a delta, which are pin 2, 3, 5, 6, 1, and 7, and 4 still being the protective earth. And if you look at the bottom, this shows, 1, 3, 6 together and 2, 5, 7 together. So this gives you the 2 line connections, right, for single phase. So this shows you how we, configure the supply cord to mate with a universal 7-pin positronic connector. This here on the bottom is the rear view of the power shelf, where we are seeing the 2 positronic connector we talked about here in the back, and the bar clip connector, which is the output connector right in the middle. So now here we will dive a bit into the design details. The shelf uses hot dip galvanized steel. The shelf has the unique feature for smooth rectifier and PMC insertion, and this is accomplished by 2 critical design aspects. Okay, so the base. So if you're looking at it, the base has a lengthwise embossing, which what it does is it increases the IXX, which is a measure of the bending stiffness along the x-axis, and this reduces the bending along the depth. Okay, the shelf also has here, as you see here, a crosswise embossing, which increases the IZZ, which reduces the bending along the width. And IZZ, as we know, is a measure of the bending stiffness along the z-axis. The vertical dividers are riveted. Actually, all metal joints are riveted except the rear cover, which is screwed. So now we will dive a little bit into the analysis. So we have done finite element analysis to validate the mechanical performance of the shelf. The finite element analysis enables us to study the impact of deflection under the PSU weight, and also the impact of shock and vibration. As we know, each PSU is about 2.8 kilograms, and there are 6 of them, so which it is approximately 17 kg, which is an important factor. So the picture here shows, the finite element analysis as it was done, and here are the results. Now, on the bottom, we are going to see the latch and FEA, which was performed on that. Latch has 2 very important functions. It has to move to disengage, and not so much that it yields. So no yielding is confirmed by FEA. We need to balance the latch design, right? As we talked earlier about these 2 functions. So fine balancing of the latch design is achieved and confirmed by the FEA. So that's what we talked about here. Now moving on to the next slide. Shelf is primarily a passive element. We need to make sure that the components and the material work properly in the presence of preheated exhaust air as it moves from the rectifiers. Not only that, we also need to look at the self-heating of the output bus bars. Okay, so here, if you see here, the picture on the right shows how the bus bar temperature is even, and the picture here on the left shows, the current density and the self-heating, and the different blue, red, and the yellow colors show the different temperatures. See, the red here points the bus bar transition to the output. The top picture here shows the back panel and the uniformity of the temperature. One more thing to mention is the test conditions are critical for all this, and and it mentions that, and this should be taken into account. When we perform this analysis, we have taken the ambient temperature of 45 degrees, which is on the higher end for all these calculations. And the rectified dissipation is about 105 watts, and we are assuming 15 CSM of the airflow. Moving on to the last part, for scalability and control options, shelf by itself is designed to be easily scalable to the high power. We have taken that into account because we have to keep in mind that the rectifier power may be increased in the future and the shelf power may be increased in the future. So, and that can be done by proper selection of the input connectors, the rectifier connectors, output bus bar thickness, and the output connectors. As we all know, the PMC design is in progress right now, and once the design files are released, the PMC can be, further, and we can do the same PMC, or it could be enhanced by adding additional monitoring functions, control functions, and communication options. So with that, I will conclude my talk, and I will hand over the mic to my colleague, Lam Vu from Light-On Technologies, and who will take you all through the power supply and the PMC.
My name is Lam Vu, and I will talk about the PSU and the shelf controller. The PSU is a 3 kilowatt rating with a 50 volt output. And the dimension of the PSU is 73.5 by 520 by 40 millimeter. So it will fit into 1 OU. The input voltage range will be 208, 240 to 77 nominal. And the power supply will be able to produce full load output from 185 volt to 305 volt. And it will also cover both the 50 hertz and 60 hertz frequency for a worldwide application. The maximum input is 17 amp, and we will be able to accommodate the ITIC requirement, at least at 230 and 240 volt input. Efficiency, we are targeting 97.5% peak with 96.5% efficiency over the range of 30% to 100% load. And output voltage is a fixed 50 volt, but with a narrow adjustable range for testing in the system together with a 48 volt battery bus. And the current output is a 60 amp max. And as Ralph talked about before, that we will have both active current share and droop share of 1% of the nominal voltage. And the power supply will have operating temperature range from 0 degrees C to 55 degrees C. And all the input-output connection will be from the back of the power supply. And we use the Amphenol Ultra Blade HD connector. And the power supply will have a communication using PM bus linked to the power shelf controller inside the shell. The power supply can coordinate with other power supply inside the shell for startup and for overload protections and restart without any need for a shell controller, because the shell controller, the PMC in definition, is only for communication and reporting only. For the startup and restart, there will be a pin that connect all the power supply together, and I call it a sync start. And at the startup, all of the PSU will monitor this pin and wait. I mean, this pin is bidirectional, so when the power supply is not ready yet, it will pull this pin down, and when it's ready, it will release it. So at startup, all the PSU will look at this signal, and when this signal is ready, they will start. But the power supply, once it starts, it will not monitor the signal anymore, so that when you insert or extract the power supply when the shell's already running, then it will not affect or it will not disrupt the output when all the power supply is already running. In current sharing, we have both active current sharing and group share. The active current sharing, of course, is a pin that send out the signal that represent the output current of each PSU, and it is diode OR on this active share bus. And all of this share will not need any type of supervision from the shell controller. Okay. And the group is size is at 1% of nominal voltage over the output current range. So, and the power supply will be able to handle 50% load with plus and minus 1 volt deviation, and it will be able to handle a slew rate of 1 amp per microsecond. Power supply will include protections, with overload protections, and so when the power supply encounter overload, it will go into constant current mode until the output voltage drop to about 80% of nominal values. I mean around 40 volt, and it will shut down. And the power supply will recover and do that for 3 times before it will shut down if the condition persists. And the power supply also have overtemp protections and over voltage protection. And next I will talk about is the shell management controller. And this dimensions is particular for LIDON. We will have to, all 3 of vendor will have to agree on a certain common size. So for us, this size is 50 by 273 by 40 millimeter, and it's power from the output 48 volt or 50 volt rail. So that means inside the controller, it has a isolated power supply to convert 50 volt or 48 volt to logic level. And the shell controller will talk to the power supply through PM bus on the I2C physical layer. It's gonna have 2 channels, and each channel can talk to 6 power supply. And communication to the rack management level, it has 2 mechanisms. One is through Ethernet port, and also the other is through a Modbus through a Modbus. On the Ethernet port, it can support many different protocol. I list some of them here: IPv4 for IP address control, HTTP or HTTPS. It also support SMTP, which is email, and it also support SNMP, which is Simple Network Management Protocol. On the Modbus, it has a port that has RS485 a physical layer for Modbus protocol, but it can also provide Modbus protocol on the Ethernet connector by TCP/IP. And the shell controller purpose is only for reporting function only. So when the shell controller is not there or is there, it will not affect the shell ability to provide power. Okay, and this shell controller is common for both the 1U and 2U. And beside all the communications with rack management controller, the shell also have the user interface that allow the user to connect to the shell locally to monitor during the setup. And it has a JSON based web GUI, and it also have a command line interface using SSH. So this is the end of our presentation, and we thank you for your attention to our presentation. And after this, we will have 10 minutes time for question and answer. Thank you.
before a failure happens. So currently, this is not requested by the PSU specification. Yeah, if someone requests this, there need to be installed some more memory to store this this last events. It's doable, let's say, but it's not planned yet.